Hello and welcome to this video. I am Karnesh Chauri and today we'll look at time in Linux. We'll look at time related commands, system calls, alarms and clock time synchronization using the NTP. And we start with the commands. There are two clocks in the system. The first is the real-time clock RTC, also known as the hardware clock or the CMOS clock. The real-time clock is powered by a battery and keeps on running even when the system is turned off. The second clock is the system clock, also known as the kernel clock or the software clock. The system clock is maintained by the kernel based on the timer interrupt. When the system starts, the system clock is initialized from the real-time clock. After that, the two clocks work independently. So, there is a hardware real-time clock and a system clock. And there is a popular saying, a man with a watch knows what time it is. A man with two watches is never sure. So, what is the time in your Linux system? There is room for confusion, which has been brilliantly set aside by computer scientists who have invented the network time protocol, the NTP. There are trustworthy network time servers on the internet. A computer connected to the internet can simply ask any of these servers about the current time using the network time protocol and synchronize its clock. Then we have time zones. The local time at a place depends on its longitude. Rather than having continuously varying time across the globe, the world is divided into geographical regions called time zones. All places in a time zone follow a uniform time for all economic, legal, and social purposes. So we have the local time zone for a computer, and if we give a command to display date and time, the system displays the date and time as per the local time zone. Then there is the coordinated universal time, the UTC. UTC is the primary standard of time and is within 1 second of the mean solar time at the prime meridian, that is 0 degrees longitude, and is not adjusted for daylight saving time. The timedatectl command is for managing the system clock. You can query and modify the system clock and its settings using this command. We can see the current setting of the system clock and the hardware real-time clock with the timedatectl status command. The output of the timedatectl status command gives the local time, universal time, real-time clock time, the time zone. Our time zone is etc/UTC, which is UTC plus 0 hours and 0 minutes. The system clock is not synchronized, but the time syncd service, which is a part of systemd, is running. Our real-time clock's RTC is not in local time zone. It is in UTC as it should be. Suppose we want to change our time zone. We can list all the time zones with the timedatectl list time zones command. Then we can select the time zone value we want to set, and we can execute the timedatectl set time zone command. We can set the system clock date and time using the timedatectl set time command. The date and time should be in the YYYY, MM, DD, HH, MM, SS format. And since there is a space between date and time, it should be put inside quotes. For example, timedatectl set time 2020 0402 13 59 59 sets the desired time. However, the correct date and time are critical for a system's operation, and it is best to synchronize the system clock with the network time server using the NTP. And we can do that with the timedatectl set NTP command. For example, sudo timedatectl set NTP1 sets the synchronization. It enables and starts the systemd time syncd service, which is a lightweight, minimalistic implementation of the NTP. It should be sufficient for most purposes. However, if you want full-fledged NTP, you should disable systemd time syncd service and install the NTP package with the command sudo apt-get install NTP. And finally, we have the date command that prints date and time for the local time zone. You can pass -u option for the UTC. We have concentrated mostly on the system clock till now. Now we'll look at the hardware clock. The basic purpose of hardware clock is to provide time to the system clock to get started at the time of system boot. At first, the personal computers did not have a hardware clock, so one had to enter time after the system boot every time. Occasionally, one would forget that, resulting in all files created in that session to have the creation time close to January 1st, 1970. Then, as an improvement, personal computers started to come with a hardware clock, relieving the user about the need to enter time manually. However, in a few months after installation, the hardware clock would either be ahead or behind the actual time. So one had to manually correct the time once in every 3 months or so. Later on, network time servers became common and almost all computers had internet connectivity and time synchronization became automatic. HW clock is the hardware clock management program. The usage is HW clock function followed by options. The -R option prints the value of its time in the ISO 8601 format. The time is shown as the local time even if the time is set as the UTC in the hardware clock. The hardware clock is not accurate. As time passes, it loses or gains time. However, it gains or loses the same amount of time every day. This is called systematic drift. Using the systematic drift value, we can calibrate the hardware clock. There is a file named /etc/adj time which keeps the historical information regarding the adjustments to the hardware clock. The HW command has an adjust function that helps us apply the systematic drift calibration to the hardware clock. We can adjust the hardware clock for the systematic drift with the HW clock -adjust command. Some other important commands for the hardware clock are HW clock -s or HW clock -HC to sys for setting the system clock from the hardware clock. Similarly, we have HW clock -W or HW clock -sys to HC for setting the hardware clock from the system clock and updating timestamps in the /etc/adj time file. And finally, we can set the hardware clock with the -set option. HW clock -set -date is equal to YYYY/DDHH/SS command. For example, we set the hardware clock to 2020-0404-22-2315 and we can check it with the HW clock -R command. We now come to the programming part of this video and we look at the system calls. There are two kinds of time, calendar time and execution time. We'll first look at the calendar time. The most common type for calendar time is time T, which is the number of seconds that have passed since the epoch January 1st, 1970, 00 hours, 00 minutes and 00 seconds UTC. And we have the time system call, which returns the number of seconds that have passed since the epoch. The time system call takes an argument which is a pointer to time T. If this argument is not null, time is also stored in the location pointed by this pointer. However, the recommendation is to pass null as the argument always and use the returned value as the time. Next, we have the structure struct timeval, which has two members tvsec and tvusec, that is seconds and microseconds since epoch January 1st, 1970, 0 hours, minutes and seconds UTC. And we have another structured struct time zone comprising of TZ minutes west of Greenwich and TZ DST time, type of DST correction. The system called getTimeOfDate takes in pointers to these two structures as arguments and returns the values filled in these structures. Actually, the second parameter is obsolete and the call should be made with null as a second parameter. So getTimeOfDate returns seconds and microseconds since epoch in the structure pointed by the first parameter. We have seen the importance of type time T, the number of seconds since the epoch. But we are all used to date and time as day of month, years, hours, minutes and seconds. That is, time should be broken down into these data elements. And sure enough, we have a structure struct TM which has got seconds, minutes, hours, day of the month, year, and some more fields for more esoteric use cases. And there are conversion functions. Local time converts time t to the local broken down time. It returns a pointer to struct tm with a pointed location having the local broken down time. Local time r does the same, but as an additional parameter, you have to pass a pointer to the struct tm, and the results are also copied in the location pointed by this pointer. Similarly, gm time and gm time r convert time t to the corresponding UTC broken down time. Next, we have the mk time function, which converts broken down local time to type time t, that is, number of seconds since the epoch January 1st, 1970, 0 hours, minutes and seconds. Time is also represented by a local time string like WED, APR, 8, 22, 56, 40, IST, 2020. The ctime function converts time in time t format to a local time zone time string. It returns the converted time string. The ctime r function works just like the ctime function, except that it has a second argument, which is a character pointer. The caller has to pass a buffer as a second argument, and the converted time string is also written in this buffer. The ASC time function converts a broken down time to a corresponding local time string. It returns the converted local time string. The ASC time r function is just like the ASC time function, except that it has a second argument, a character pointer. The caller has to provide a buffer in this second argument, and the resulting string is copied in this buffer also. We have gone through the calendar time in some detail. Now we look at the execution time. The execution time is useful from the operating system point of view. When a process is running, it alternates between the user and kernel modes of operation. In the user mode, it executes the code of the program. Now suppose the process needs to write to the disk or read from a network socket. The input-output devices are available for use by any process. If multiple processes start writing to the disk without any arbitration, there would be chaos. So when a process wants to write to the disk, it executes a system call and the process starts executing in the kernel mode. That is, the kernel executes on behalf of the process and writes to the disk. Once the system call is over, the process switches back to the user mode and keeps on executing code. And for how long did the process work in the kernel or system mode? These are topics of execution time. Next, suppose you need to do some periodic work. The process should sleep for say a minute and then do some work. What you really need is the process should pause and the alarm should wake it up after a minute. So the timing of this interval, 1 minute, is another aspect of execution time. The kernel keeps a software clock for keeping track of execution time. The unit of kernel's clock is jiffy. The value of a jiffy is 1 divided by hz, where hz is a compile time kernel configuration parameter. hz can have value like 100, which makes a jiffy equal to 0.01 second. Other possible values of hz are 250, which is the default, and 300 and 1000. However, this is all internal to the kernel. For the external world, the kernel has a constant user hz, which has the value 100. We can get the value of user hz as sysconf _sc _clk _tck. The time system call reports the execution time in units of 1 by hc clk tck. As I said earlier, there are two types of execution times: user time and system time. User time is the time processor has been working directly for a process. System time is the time kernel has been doing privileged work for a process. Struct TMS contains the user and system times for a process, followed by user and system times of its children. The time system call gets the user and system times for a process and its children. The calling program passes a pointer to a struct TMS, and these times are stored in that structure. The unit of these times is the clock tick, that is 1 by _sc _clk _tck. Let's look at the structure for resource usage struct rUsage. The first two members are struct timeval, which is time in seconds and microseconds. These first two members are for user and system times. Then we have long integers for maximum resident set size, integral shared memory size, integral unshared data size, integral unshared stack size, page reclaims, soft page faults, hard page faults, swaps, block input operations, block output operations, IPC messages sent, IPC messages received, signals received, voluntary context switches, and involuntary context switches. A pointer to the structure is a second parameter to the system call getRUsage, that is, get resource usage. The first parameter who is the answer to the important economic question, for whom. If the value of who is rUsage self, the resource usage for the calling process is returned in the structure pointed by the second parameter. If the value of who is rUsage children, the resource usage for all children of the calling process that have terminated and have been waited for is returned. The children include grandchildren and further descendants as well. The only condition is that they should have terminated and have been waited for. And finally, if who is rUsage thread, the resource usage for the calling thread is returned. And we have the clock function, which returns an approximation of processor time used so far by the calling process. The return value from syntax point of view is clock t, but the semantics is quite different from the earlier use of clock t. The system has a predefined constant clocks per sec. To convert the value returned by the clock function into seconds, we need to divide it by clocks per sec. Now clocks per sec is mostly defined as 1 million in Linux systems. So we can say if clocks per sec is 1 million, the value returned by clock function is in microseconds. Now we come to the last part of our video. In this part, we look at alarms, sleep, and high resolution timers. And we start with the alarms. An alarm is a signal. Signals are notifications that are sent asynchronously to a process. The default action for most signals is to terminate the process. A process can install a signal handling function to change the default action. When the signal comes, the signal handling function is executed instead of the default action. So a process first installs a signal handling function for alarm using the sig action system call. The process first defines a struct sig action and sets as a handler to the signal handling function for alarm. It then makes the sig action call using sig alarm as the first parameter and a pointer to the previously defined sig action structure as a second parameter. The third parameter can be null. After this, it can set an alarm using the alarm system call. The alarm system call has an integer parameter which is number of seconds after which the kernel should alarm the process. Any previously set alarm is cleared. If 0 is passed as the parameter, no alarm is set. So to clear any previously set alarm, call alarm with 0 parameter. When the alarm comes, the signal handling function for alarm is executed. We have a function called sleep with an integer parameter indicating the number of seconds the calling process wants to sleep. Normally, the process is put to sleep for that many seconds and returns with the value 0. However, the process might get interrupted with the signal it has not ignored, and in that case, sleep returns with a value indicating the number of seconds the process has not been able to sleep. Now, sleep is a function possibly implemented with POSIX alarm system calls underneath. So, it is not a good idea to mix sleep and alarm calls in a program. Next, we have useSleep function. useSleep is similar to sleep except that the usec parameter is in microseconds. The process sleeps for usec microseconds and maybe a little longer for the time is required to process the function call, and also granularity of underlying system timers comes into play. And of course, like all calls, it might also get interrupted by a signal. Nanosleep is high resolution sleep. The caller has to define two struct time specs and pass pointers to it. A struct time spec contains two members, namely tvsec, which is in seconds, and tvnsec, which is in nanoseconds. tvnsec should be between 0 and 999,999,000 and 999 nanoseconds. Nanosleep puts the calling thread to sleep for the amount of time specified in the first parameter struct time spec pointed by REQ. If it is able to sleep for that much time, it returns 0. But if nanosleep is interrupted by a signal, nanosleep returns -1 and ERRNO is set to EINTR. And if the second parameter RAM is not null, the unslept time is returned in the structure pointed by RAM. Now nanosleep is better than sleep and use sleep because, as specified by POSIX.1, it is not built using signals. However, signals can still interrupt it. Also, if the amount of sleep is not an exact multiple of the underlying clock resolution, the sleep round time is rounded off to the next multiple of clock resolution, and also some time is required to reschedule the thread. And for these reasons, nanosleep might sleep a little longer than what was originally desired as per the time spec structure pointed by the first parameter REQ. Before Linux 2.6.21, the accuracy of timers and sleep call was determined by the size of Jiffy, which is 1 by HZ, where HZ is the kernel compile time parameter. So if HZ was 100, the clock resolution would be 0.01 second, and if HZ was 1000 Jiffy, the smallest time measurable by the kernel would be 1 millisecond. This changed with Linux 2.6.21 as higher resolution timers became available if the kernel was built with compile time configuration parameter config high-res timers equal to Y. You can check whether the kernel you are running supports high-resolution timers by executing clock get res system call in a program, or check up resolution entries in /proc/timer_list. We have seen the alarm system call. Now we have interval timers that are similar to alarm but a little more advanced and finer. The major difference between alarm and interval timers is that alarm is one time, whereas an interval timer can be periodic. That is, it can keep on repeating the alarm unless specifically stopped. iTimer real decrements in real calendar time. When it becomes 0, SIG alarm signal is sent to the process. iTimer real uses the same clock as alarm. It also sends the same SIG alarm signal to the process. So we should use either alarm or iTimer real and never mix calls to the two in a program. iTimer virtual decrements in a process's virtual time. That is, it decrements when the process is executing in user mode. When it becomes 0, SIG-VT alarm signal is sent to the process. iTimer prof decrements when the process is executing in the user mode or when system is running on behalf of the process in the kernel mode. When it becomes 0, signal SIG-prof is sent to the process. iTimer prof is used by profilers. iTimer system calls use these structures. Struct timeval has got tvsec, which is seconds, and tvusec, which is in microseconds. Struct iTimerval has two timeval structures. Struct IT interval is the next value for the iTimer, and IT value is the current value of iTimer. That is, it will decrement IT value. When IT value becomes 0, it sends the relevant signal. Also, it initializes IT value from IT interval for the next timer operation. If IT interval is 0, IT value also becomes 0 and the iTimer stops. There are two system calls for the interval timer. The first is get iTimer, the first parameter which identifies the interval timer, which can be iTimer real or iTimer virtual or iTimer prof. The get iTimer call gets the value of the timer in the iTimerval structure pointed by CURR value. Similarly, set iTimer sets the concerned iTimer with the iTimerval structure pointed by new value. If the iTimer was already on, current values are copied in structure pointed by old value, and then the iTimer is set from the structure pointed by new value. There are multiple high resolution clocks. Clock real time is the system-wide real-time clock which can be set by the super user. Clock monotonic cannot be set and gives time since some is unspecified point. However, clock monotonic is affected by ADJ time and NTP adjustments. Clock monotonic raw is similar to clock monotonic but is not subject to NTP or ADJ time adjustments. Clock process CPU time ID is the clock for the process. It gives the time consumed by all the threads of a process. Clock thread CPU time ID is the clock for a thread. If you look at the manual for clock get rest system call with the man clock get rest command, you'll find some more clocks. Of these, clock real time is standard and rest are implementation dependent. And we look at the system calls related to the clocks. These calls make use of struct time spec, which contains tvsec in seconds and tvn sec in nanoseconds. The first call is clock get rest, which gives the resolution of clock identified by the first parameter CLK ID. So this call lets us know whether the clock is available or not, and if it is available, the resolution is returned in the struct time spec pointed by res. Clock get time is used to read the value of clock identified by CLK ID. The value of the clock is returned by the struct time spec pointed by TP. Clock set time stores the value pointed by TP in the clock CLK ID. We can write a small program to find and print resolution of clocks. When we compile and run the program, we find that all the clocks have 1 nanosecond resolution. POSIX timers use the real-time extension signal mechanism, the RTS, to send signals to processes. POSIX timers use the SIG event structure to specify what signal and other information will be sent. In the SIG event structure, the first member is SIG EV notify. The value of SIG EV notify should SIG EV signal, that is, generate a signal. SIG EV SIG NO is the signal number to be used, and SIG EV value can be the same signal number. The next members are not relevant if SIG EV notify is SIG EV signal and SIG EV notify thread ID is the ID of the thread to be notified. A POSIX timer is created with a create timer call. The first parameter clock ID identifies the clock to be used. The next parameter is appointed to SIG event structure, which tells about the signal to be generated once the timer goes off. If null is passed as a second parameter, SIG ALRM is generated and the timer ID is returned in the location pointed by the last parameter timer ID. Struct time spec has got two members, tvsec, which is in seconds, and tvnsec, which is in nanoseconds. Struct iTimer spec has two time spec structures. After timer create, we can arm a timer, which means we assign it a time interval and the timer gets started. The system call for this is timer set time. The first parameter timer set time is timer ID received in an earlier timer create. The third parameter new value is used to arm the timer. If new value pointer IT value is non-zero, the timer is armed, that is, it is started with the IT value as the initial interval of the timer. If the timer is already running, its time interval gets overwritten. If IT value is 0, the timer is disarmed. The second struct time spec in new value is IT interval. After the timer goes off, its IT value is reinitialized from IT interval. If IT interval is 0, the timer was in fact a one-shot timer and it gets disarmed. Normally IT value is interpreted relative to current time. However, you can pass timer ABS time in flags, the second argument, and IT value is considered absolute time of the relevant clock. And timer goes off when the relevant clock reaches that time. If the absolute value is specified in IT value has already passed, the timer goes off immediately and overrun count is set accordingly. If old value pointer is not null, the previous time interval is returned in old value pointer IT interval, and old value pointer IT value returns the time left in the timer to expire at the time timer set time call was made. Next, timer get time returns the current value of the timer in the structure pointed by CURR underscore value. CURR underscore value pointer IT interval returns the timer interval. CURR value IT value gives the time left for the timer to go off. If this is 0, the timer must have been disarmed. Similarly, if the returned CURR value pointer IT interval is 0, it must have been a one-shot timer. Both timer set time and timer get time return 0 on success and -1 on error, with error number set accordingly. Timer delete deletes the timer defined by the timer ID. There can be delays between a timer signal is generated and it is delivered. The delays can be because of scheduling delays or a signal might have been blocked, etc. Timer get overrun system call gives the number of times the timer has gone off since the last signal was generated and was being delivered to the process. As an example, we look at a program with 100 microseconds timer. We have a global variable timer1 and we have the main function. This program prints time every 100 microseconds, which is 0.1 millisecond and 1 upon 10,000 seconds. We define a signal handler for sig alarm, which is the print time function. When sig alarm comes, the print time function should be executed. We create a timer for sending sig alarm. We create a timer with timer create and we set time with timer set time. The timer interval and timer value both are 100 microseconds. Now time is set. We need to run this program for some time, say 1 millisecond. In 1 millisecond, we should get about 10 timer1 alarms. To set the process running for 1 millisecond, we create a one-shot timer, timer2, to go off in 1 millisecond. This timer should send the sig RT-min signal. We create timer2 with timer create. It is one-shot timer, so timer interval is 0 and timer value is 1 million nanoseconds, which is 1 millisecond. And we wait for timer2 to send sig RT-min signal. In the meantime, when sig ALRM comes, the function print time prints time. We can compile this program. We need to link with the real-time library with -LRT option. GCC -time.c -o -time -LRT and we run the program /time. We have 10 lines of output, and since the program runs for 1 millisecond and each sig ALRM comes every 100 microseconds or 0.1 millisecond, this is okay. The first column is seconds, which is constant. The second column is nanoseconds. Since our timer goes off every 100 microseconds, the second column should vary by 100,000 nanoseconds. The difference between consecutive values is close to 100,000 nanoseconds. Why is it not closer? If you look at our signal handler, we are getting the sig ALRM signal and then looking at the clock monotonic and printing its value. And there may be scheduling variations and variations in I/O and things like that. With clock nanosleep, a process can specify the sleep interval with nanosecond precision, and also it can specify the clock it wants to use for timing the sleep. The first argument specifies the clock. The clock ID can be either clock real time or clock monotonic or clock process CPU time ID. The third parameter is the requested sleep time in seconds and nanoseconds. The flags can be 0. That means the request is relative to the current value of the specified clock. If flags is timer ABS time, the request is interpreted as absolute time in the indicated clock. If flags is timer ABS time and requested time is less than or equal to the time in the indicated clock, clock nanosleep returns immediately and the calling thread is not put to sleep. If the sleep is interrupted by a signal and flags is not a timer ABS time, the unslept time is returned in the structure pointed by the last parameter remain, and the calling thread can go to sleep again for the remaining time if it so desires. After successful sleep, clock nanosleep returns 0. If there was an error, -1 is returned and error NO is set to the error. We can write a small program to try nanosleep. In this code snippet, we do a clock nanosleep for 100 microseconds and we check time before and after clock nanosleep. A difference of 2 clock times tells us roughly how much time we have taken for this sleep. We have definitely slept for 100 microseconds and the time taken to check clock twice and the time to make clock nanosleep call is about 65 microseconds. And if we don't sleep at all, that is make call to clock nanosleep with 0 time, we get the results which tell us that sleep or no sleep, it takes about 65 microseconds to make 2 clock get time calls and 1 clock nanosleep call. A lot of information given in this video is available at calendar time under Linux https://tinyurl.com/cal-time Synchronize your computer's clock using the NTP https:/tinyurl.com/sync-ntp HW clock, the hardware clock query and set program https:/tinyurl.com/HW clock Linux process execution time https:/tinyurl.com/exec-time Alarm, sleep and high resolution timers https:/tinyurl.com/high-res-timers. And we come to the end of this video. Thanks very much for watching. Take care and stay safe.